Hi, this is Eric Grolke, Chemical Engineering, University of Kentucky. This is a description of a toll processing distillation problem, one that we're going to do on one of the days for our workshops for the process simulator ChemCAD. This is a problem which is somewhat similar to the distillation experiment in laboratory and should help us understand what's going on. In this particular scenario, we're going to pretend that we are a toll processing company and we are taking the methanol isopropanol solution provided by a client firm, toll processing it into materials which can be recycled or resold on the open market. So we're going to talk about what a toll processor does. We're then going to talk about how we would assess the economics and the markets and other demands for these products, and then do a little bit of work to show you how we might start to focus on the objectives that a toll processor might have and the differences in the economics and considerations that we would have doing this process as a toll processor. So here we go. First, let's talk about what a toll processor is. Toll processing is becoming increasingly important in the chemical business because a number of firms discover that they don't have the technology and people in-house to do some of the new things that they need to do to be competitive. So outsourcing continues to be important. The idea is for the one firm to provide some capability, capacity, or a location to another, and what the result is that the company which is buying the toll processing services does not have to do this in-house. They can do this on a flexible basis, and it's extremely useful. Often the toll processing company has some specialized equipment, or they may have advanced quality testing devices. They are paying attention to regulatory requirements of the materials that they are working with. They might be able to store raw materials, and they also may serve new geographical markets for the company. What's our problem? Well, let's suppose that we have a client, a polymer company client, which has developed a new process that generates a waste stream containing about 50% methanol, 50% isopropanol with a small amount, less than 1%, in butanol. The company would like to recycle the methanol and isopropanol, but does not have the engineering expertise or facilities on site, so this is a new process. Management has decided to use a toll processor to treat the stream and return separated solvents back to it for sale or reuse. Our toll processing company is supposed to propose how to do this and provide a quote to the polymer client. We happen to have an 8-tray distillation column that's well instrumented with several possible feed trade positions. There's also an additional 8-tray column that could be used if needed. If so, if we were going to use both columns, it would be most convenient to feed the 2-column system in between the two. That is, feed at the bottom of the top column or the top of the bottom column. As a toll processor, we're going to be paid to convert the solvent mixture into 2 streams that will be returned to the company. We will not own the entering fluids or the produced solids and solvents. Those will not appear on our economic evaluation. We are also only going to charge for our costs in doing the conversion. That's typically what a toll processor might do. We also are going to analyze this process using a project triage analysis to look at factors that are going to be important to the design. When we are looking at new processes in the chemical business, there are 5 elements that are often critical to their success. They include what is the demand or market, what are the problems or challenges in operating or using the systems and the process, what is the intellectual property that's going to be needed to cover this, are there any regulatory issues, and if we commercialize this, how will that go? Do we have the people in place to do so? Not all of these elements apply equally well to every scenario, but we are going to apply them to this particular one. Here are some thoughts that would affect the various elements, various factors of this product triage approach. Number one, demand, operations and use, intellectual property. I've put on the right-hand side some elements or some thoughts on what you would think about as you were assessing the problems with demand, operations, use, regulatory, and commercialization. I'm not going to go through these in detail. We will discuss these for this particular problem. Here are a comparison of two product options. These were medical device examples. These were two different case studies that a company was looking at for potential commercialization. So we've applied these tools to these two different products, case study A and case study C. A number of 6, which would be on the outside of the pentagon, would be a very favorable condition for the company. So we would like to have projects that have 5s or 6s if we could. As you can see for case study A, there's not very much demand. The clinical use, in this case equivalent to operations, is going to be difficult. There's modest intellectual property coverage, and that's great, but there are some serious regulatory issues and commercialization is not clear. You can see that by the two average scores in the forced rankings. In contrast, case study C has got a relatively high demand. The clinical or operating use looks like it's favorable, and average intellectual property coverage, but not very much regulatory concerns, and a better pathway to commercialization. So we're going to try to do the same thing with this particular problem. So here are some factor assessments for the innovation for this particular process. In terms of demand, what product specification should you adopt that best serve the polymer client? That is, what should you make for the client? Are you going to make just a mixture? Are you going to try to purify into pure methanol in pure isopropanol? What's the product specification going to be? How much of the solvents are you going to recover into each stream? In terms of your operation and use of this process, how will you use the available columns, and what will the reboiler duty, the condenser duty, and the reflux be? These are important questions because most of your costs are going to be the operating costs, and in particular the costs of steam and cooling water to do the separation. Because these are well-known solvents and it should be fairly straightforward to separate them, we don't expect there to be much intellectual property associated with this problem. Regulatory issues should be modest. We know a lot about methanol, we know a lot about isopropanol, and these should be easily handled in our operations. One question for commercialization would be, could our company design columns that would scale up or scale down from the one we're about to propose, because the manufacturer may have sites at different geographical locations, and it would be much better to do this process separation locally rather than to ship everything to one site nationwide and do it there and then reship the products. So we have to pay attention to transportation costs, and our polymer client would be interested in this potentially. Okay, so what we need to do is do an initial rating on this process for demand, operations, use, IP, regulatory, and commercialization. I show again the pentagram, and here's what we might do for rating this problem. In terms of demand, it would be much better to provide our client with technical grade products if possible. That would give the client the most latitude for resale or recycle. In terms of operations and use, our problem as the toll processing company is to make two products at a minimum processing cost. We already have the columns. Those contribute only a little bit to the total cost of doing this operation. The most important thing is our process labor and our steam and our cooling water. In terms of IP, these are really well-known materials. We might generate some trade secrets. It's not likely, but we would have to see when we're all done. In terms of regulatory, as we've said before, all solvents have modest environmental health and safety hazards, so we should be able to control those easily. In terms of commercialization, if we can provide our polymer client with either scaled up or scaled down process designs, this would be a second revenue stream for us and would provide a secondary product. That would be something we'd be quite interested in. So here's an example product triage analysis by the students who were doing this problem last year in 455. I took one of the reports and I show their product assessment. In the pentagram here, operations and use is given a very good rating. That is, we think it's going to be fairly easy for us to control this process. The demand is reasonably good. We know that the company wants to recycle these materials. They don't want to send it off to a landfill or something else like that. So they are being responsible in trying to solve this problem. We've given ourselves a good ranking for commercialization because of the potential for a secondary product. We think we understand the regulatory issues very, very well, but there's not very much intellectual property. And on the next slide, I've got a description from the students themselves in terms of how they saw ranking for this. So what you might do is you might just read this over and think about their thought process, which is slightly different than the one I provided to you. But this is something that the students were able to do last year, and we would expect you to be able to do on process problems in this course. Okay. Now we get to product specs and prices. If you're going to return separated solvent to the polymer client, it would really be best if we can provide them with products that meet current specifications in the market. That is, if we could make research grade methanol or research grade isopropanol, that would have a higher value than technical grade, and it would certainly have a higher value than a reprocessed solvent. Technical grade specifications for both of these solvents is about 99+% pure. That is, typically they might have as much as 1% contaminants, but when we get to the process simulation, we're actually going to set a specification which is above 99.0% because we would like to ensure that our column always produces something which is sellable as technical grade. Another advantage of using a known grade solvent is that there's already a market established for this, and we know the pricing from the market. This reduces the risk to the company. So in general, when we're doing process design, we always ask the question, what's the price, what's the market, what's the risk associated with those costs? How do we get product costs? Well, here's a very nice set of guides that's been put together by Sue Smith of our engineering library. They're now the Engineering and Science Library. So she's got several things put together for us. One of them is a set of library guides specifically for chemical engineering, and I'll show you the web page on that. She's also, in the library guides, put in a section on chemical pricing. And then finally, we can get chemical prices from Sigma Aldrich. These are not going to be necessarily the best because they're for small quantities, they're not for bulk quantities. We're going to be making bulk quantity of solvent, and it would be better to use the chemical pricing available in the second reference here. So if you go to the library guides for chemical engineering, this is something that Sue Smith has put together, as I said. There is a section on chemical prices and pricing, and that's what we want to look for. That's also have sections on databases, a tutorial for using the databases, materials pricing, business and economic resources. You may need some of those over time. I'd also like to call your attention to this selected books on the left-hand side, the Encyclopedia of Chemical Technology by Wiley InterScience. This is really a great reference, and it will give you some ideas on process technology which may or may not compete with what you're proposing. So when we go to the library guides, we have three elements under pricing that are useful. Probably the most useful one here is ICIS chemical business. This formerly was the Chemical Marketing Reporter. The college used to have a subscription to this, so we could get prices very readily. You can get some price information from this. And typically what you'd like is to select a year, and typically you would select the most recent year, like 2015 or 2016, and you would search within the publication for information on your particular solvent or material. So here is something on the methanol price, and there are 3 articles there that you can go and read and get some information on methanol prices. In our particular case, we have taken a look at the prices. We do have prices for these recovered solvents if they meet the technical grade spec. So taking a look at the table, and let's start with the table right here. This is the cost for 2-propanol or isopropanol. Internationally, it's about 800 euros per metric ton. This is an international market, so it's affected by the euro and the dollar. At this particular point last year, the dollar was 1.14 to the euro. So that if I had 1,000 kilograms of 2-propanol or isopropanol, that would cost me $912, or about 91 cents per kilogram. On the other hand, the cost for methanol was about 111 per gallon. There are 3.89 liters per gallon. So I ended up with a cost of 36 cents per kilogram for methanol. I haven't read a note that this is really a 2015 price for methanol. Commercial methanol users and producers start with oxidation of methane to make the methanol. Recently, the methane prices in the U.S. have dropped, and therefore the methanol prices have dropped. And so we would expect the methanol prices to be down from the prices on this slide. Then the final table is really the important one, which is how much material do we have in process over a year? Well, if we are treating a stream which is 50 kilomoles per hour of methanol and isopropanol, so 100 kilomoles per hour total is the process stream. I've got kilograms per hour, I've got dollars for the solvents per hour, and then I have dollars per year at a yearly basis. So what you can see is that the value of our isopropanol stream is about 5 times the value of the methanol stream. This gives us a really big hint on what we should try to produce in the plant. That is, producing a quality isopropanol product would be probably a better objective than producing a quality methanol product, even though it may be easier technically to produce the methanol product. And the reason is the price. Much better price for the propanol. And the price for methanol is coming down, as we just found out. Okay, there is a small amount of N-butanol in this process. So as long as our product at technical grade isopropyl alcohol has a amount of butanol, which is say 0.1 to 0.3%, this probably would be acceptable. We will probably need to make sure that the clients that our polymer company would be selling the isopropanol to can accept material with N-butanol in it. This would be something we would, so it does reduce the value of the technical grade a little bit, but this is also a way of getting the N-butanol out of the process. If we simply recycled this material, this would eventually build up in the polymer process and could be a problem. The other thing that I've done on these slides is I've done some overall material balances for the distillation column. Here I've done it for an overall product of 95% methanol. This is not technical grade, as I said. It's less than technical grade. But here we've done this on a 100 kilomoles per hour feed basis. and we've got a value for the distillate and the bottoms. The distillate is just about 40 kilomoles per hour, and the bottoms are about 60 kilomoles per hour. And so this gives you an idea of what the overhead stream is. If it's 99% methanol and we are recovering 80% of the methanol in the distillate, the total methanol coming out would be 40%, and that is that balance. If we're going to make the bottom product, let's suppose we made a bottom product of 95% isopropanol, this is the material balance. Here we show a process in which we are going to get 95% isopropanol in the bottoms, and we're going to have a 90% recovery. That would be a good idea because we would like to recover as much of the isopropanol as possible. And then this is the updated material balance if I wanted to make a bottoms process, which would generate 99% isopropanol at 90% recovery. The reason I show this is that we are getting prepared to do a simulation. When we're going to do this simulation, it's important for us to know the overall material balances for the column. It's really going to speed our solution when we put in values for the material balances that close. I can put in material balances that don't close, and ChemCAD will find a solution, but sometimes it's slower and sometimes it's really slow. So we'd like to start out with the problem solved by hand before we go to the process simulator. Here's our simple equipment that we're going to take a look at. Here's the column. There's going to be a feed, a distillate, and a bottoms section. And we're going to start out by doing a shortcut column estimate. You could do a McCabe-Thiele if you want, but the shortcut column is fairly accurate, and it's essentially the same as a McCabe-Thiele. The team that did this for us was third time's the charm. So here are the equipment details. We have 8 trays, a reboiler and condenser, and for sizing purposes in ChemCAD, this will be 10 trays. Now there is one little hitch here. We would like to know something about tray efficiencies. The good news is, since we've been distilling materials significantly since the 1940s, we know a lot about tray efficiencies. Tray efficiencies are usually based on the materials you're distilling and not the details of the column. So what I've done is I've found in Perry's Chemical Engineering Handbook a tray efficiency graph which shows where alcohol tray efficiency are. So let's take a look at the commercial alcohol fractionation. That's the pluses, and there's a plus here, plus there, and a plus there. These are between 50 and 40% efficiency. So for alcohol separations, we expect our column to be fairly low efficiency. It's not going to be 90% efficiency, as you might hope. It's going to be more like 50 or 40% because those are characteristic values for this separation. That's really important because if we have a 10-tray column and we have only a 40% efficiency, we only are going to be able to use 4 real or theoretical trays at that level of efficiency. So that's not that much column to work with, and we should know that going in, that if we get to the process simulator, we're not going to be able to get a fantastically pure set of products coming out because the tray efficiency is so low. So basically, this is another reason for us to try to concentrate on making a technical grade product, and specifically the one with the highest commercial value. So that's probably going to be what we want to do. We'll find out when we get to the simulator if that's in fact what has to happen. Okay, now we're ready to do a little bit of work on the light board. We have a market analysis that says we'd like to make an isopropanol product at technical grade. That will be what we try to aim for when we do the simulation, and we will do that in the next phase of this video. Thank you. What we're going to do now is talk a little bit about the design of the toll process distillation system that we need to build and try to think carefully about what kind of products we want to make. So there are a couple things that are a little bit different about the problem as we've posed it. First of all, because we are a toll processor, we have a fixed column. That is, we're not going to have 20 trays or 25 trays or whatever. We have 8 trays in our column, plus a total condenser and a reboiler. So the way ChemCAD would count this would be 10 trays. The other thing that's sort of interesting is we need to decide on what the products are going to be. We're given a separation to make, but the client would like to recycle or be able to resell the solvent as a way of reducing its process costs. Obviously, recycling or reselling would be the best because they don't want to spend the money to treat this or to put it to a flare. That would be very expensive and costly to their process. And then the other thing that's unique here is that because we are distilling the same thing, we're going to have fixed tray efficiencies. Now, if you look in Perry's handbook in the section on, not on distillation, but on liquid gas process systems, it does have some very practical information and some heuristics on how to do distillation. One of the things that comes out of that discussion is that different solvents, solvent mixtures, have much different tray efficiencies. The tray efficiencies are not necessarily set by how the manufacturer does the equipment, but rather they're more set by the actual materials that you have in the column. So if you look up that material for something like an alcohol, in this case we have methanol, we've got isopropanol, and we have a little bit of N-butanol. If you look at the stage efficiencies for alcohol separations, they're actually fairly low, and they're probably between 40 to 50%. These two things taken together make a big constraint on this project, because instead of having 10 trays, I might have 4 or 5 theoretical trays. And that's going to cause constraints on how we do this project. So let's start imagining what we want to do. We've got this big cloud of a process, and here's our feed stream. And it's got methanol, isopropanol, and a little bit of butanol going in. And I want to get 2 products going out. Ideally, what I would like is technical grade methanol, and I would like technical grade isopropanol. Now, that's the one. The reality is, though, I only have a few theoretical trays. We will show this in the ChemCAD demonstration, but if you can imagine the XY diagram for this project. So here's 0 to 1 methanol mole fraction in the liquid, and 0 to 1 methanol mole fraction in the vapor. Here's the 45-degree line. And then our phase line might be this. As it happens, I'm going to feed right in the middle of the column, right about here. And so you can imagine if I'm stepping up and down the trays here, and I have 4 or 5 theoretical trays, and I fed in the middle of the column, 1, 2, 1, 2. I'm really far short of 99% methanol 99% isopropanol. So this is going to be a real challenge. So looking at these two problems, we can get an idea that we need to choose one of these two grades to focus on, and we might be able to get them. It's going to be even a challenge to get either up at the top at 99% methanol or down at the bottom 99% isopropanol. So one way we could decide on which choice to make would be to look at the costs. One of the things we described in the workup to this discussion was that the cost of methanol is much less than the cost of isopropanol. This is the more valuable product. And in fact, the price data we were using to come to this conclusion was about from a year ago. And after, in that time period, the cost of methanol has fallen. So there's even less incentive to sell this as a product. You'll get less money for it. And it's fairly volatile right now. So we think this is going to be the way to do the product. Well, how should we then set up the distillation scheme to make the technical grade product using 10 trays but with an efficiency of 40 to 50%? So let's go back to our XY diagram. If we consider a slightly different feeding system, let me erase that. And let's suppose that, let me reconstruct my vapor diagram. Let's suppose we fed right in the middle with the 50% that we've got. And then we'll say we have a trace. Feed right in the middle. Well, maybe I could get 4 or 5 theoretical trays, and maybe I could come close down here to getting a technical grade product. All right, so how would I set up the column to do that? Well, let's move over here and we'll talk about the column setup. Here's my distillation column. I'd like to feed it here. So I'm really feeding the 50% methanol and approximately 50% isopropanol right at the top. Taking off a methanol-rich product, but nowhere near 100%. And then with my reboiler down here, hopefully making a tech grade isopropanol. So one of the things that I can do, one of the things that would help me is if I feed a saturated liquid, then the vapor concentration will be up here. Maybe I could also put in a heat exchanger. We would like to put an exchanger in here someplace to heat up the feed beyond the 20 degrees centigrade that we probably have sitting in the drum or sitting in the tanker truck. And we would like to pop that temperature up if we could. That's going to help us with our heat balance on the column. Now this also affects how we do any sizing for the column. Normally we would use Fenske, Underwood, Gilliland to look at the minimum reflux and the minimum number of trays, et cetera, et cetera, et cetera. That works the best when I have a situation where I'm sort of feeding someplace in the middle and I'm expecting a good top product and a good bottom product. In this particular case, I'm not going to do that. I'm going to try to feed in the middle, and then I'm going to try to put all my attention down here at the bottom of the column to make a very pure or fairly pure isopropanol product. And so the normal things that I would do, which do very well if I'm feeding someplace in the middle of the process column, do not really apply very well here. So We will not go into the shortcut column method when we go to ChemCAD because that's not going to do very well for us. We can do better if we do material balances ourselves around the column as I've drawn it here. We can figure out approximately what the methanol-rich concentration is. I've already done for that for this problem, so when we went into ChemCAD and we started specifying keys and so forth, we had all the information we needed to properly specify this so that it ran the first time. And that's something I really encourage you to do. Make sure that you do your homework and you have spec'd the column as best you can yourself before you go to ChemCAD so that you are ready and you have a good chance of a good simulation. So just to summarize then, what we're trying to do is we're not going to go this way. We're going to go this way. We've got steam coming into the process. We have cooling water. And then we have electricity for the pump. Usually the electricity is going to be modest. Most of our costs in this particular case, because we have fixed trays, are going to be steam and cooling water. So as a toll processor, we are trying to drive down the cost of our utility. Okay, and that leads us to a key choice here when we get to the column design, and that is, what do we choose as the reflux ratio, R? We're going to make the choice that it's approximately 1.3. So why do I say that? Again, when you look at information from Perry's Handbook in the liquid gas processing area, they have a short discussion of choosing and the optimum reflux ratios for many distillation systems. This ratio is close to optimal conditions for a number of different systems. If we increase this ratio above 1.3 to try to, if I raise this to 2 or 5 or 10, yes, I could drive the purity of this process so it's very good. What do I do? What are the trade-offs for that? I'm going to use a lot more steam. I'm going to use a lot more cooling water. And so I'd rather not raise this reflux ratio very much if I can avoid it. I probably can't go too much below this because if I'm trying to reach a very tough to get target and I have any process upset, there's a change in temperature, or I lose cooling water for a while, or the steam line gets clogged, or the valve freezes. So if I have any process upset in the column and I'm at a very low reflux ratio, then I'll get very fast fluctuations in the column operation. The dynamics are not what we need. So this ratio of about 1.3 has been proven by a number of different operations. You can go away from that if you want to, but then you have to make sure if it's lower that you can control upsets, and 2, if it's higher, that you can stand the extra utility costs that you're going to get for doing that. So what's interesting about this problem is that we're trying to reach a goal that's going to be fairly tight. We are going to have to set up the column in an unusual way because we don't have many trays. And if we do that, we should be able to get technical grade, but it's going to be a push for us. So now we're ready to go to ChemCAD and see exactly what happens when we put this information into the process design. We've talked about toll processing and a specific problem in which we're going to receive a blend of methanol and isopropanol, and we're going to try to make some products that we can either sell or we can give back to the manufacturer for recycle. As you recall, there's just a touch of 1-butanol in the process, and so we need to pay attention to that as well. So what we're going to do now is to start building the flow sheet in ChemCAD that will solve the process. So what we'd like to do is start by opening up the program, and hopefully the program will be open on your laptop or desktop as you're following this lecture. So let's go right to the software if we can. Here is the ChemCAD 7 program. On the left-hand side is a series of choices that we have for manipulating the process. This is an example of the process we're about ready to build. We're going to have a feed stream. We're going to heat that up to the conditions of the entry point in the column using this heat exchanger. This is a tower distillation column, and we're hoping to get a top stream, which is a mixture of propanol and isobutanol, and a bottom stream, which is fairly pure in isopropanol. We're going to feed this at the top because we only have a total of 10 stages here, and in order for us to get a very pure product, we're going to need to have as many stages between the entry point and the exit of the isopropyl alcohol as possible. So this is what we're going to build. What we're going to do is start from the very beginning. We'll start with a new file, name it, and go through all the steps we would need to go through to set up the process. So we're just going to get rid of the old file. The first thing to do here is to save this file. So we're going to save it as toll processing example. And it'll go right into our set of programs that we're saving. The first thing we usually want to do when we start one of these exercises is to set the engineering units. So you have a choice between English units, common SI, formal SI, and metric. We're going to use common SI today for this particular problem. We'll keep the temperature in centigrade, we will keep the pressure in bar, and I think that will be all we have to do. So let's just make that choice of common SI and say OK. The next thing we'd like to do is to go into the thermophysical properties, and we want to select components for this problem. So we will click on Select Components. What we can do, if we happen to know the ChemCAD ID number, we can type that in, or if we can use the name, we can type that and find it in the database, and then we will select it by clicking on this entry button here. So what we've got is methanol, isopropanol, and 1-butanol. Normally I like to enter the components in order of their volatility. That helps us think about how we might be able to separate them later. So let's start out by entering methyl alcohol. And so here's methyl alcohol or methanol. We can use either one of those two. Those are the same. Those are just two different names. And we'll enter it. It appears as a selected component. Let's go for isopropanol now. And there's isopropanol. Enter it. And then the last one would be N-butanol. We could also type in 1-butanol or just butanol and we would get the same thing, because you can check to see that the CAS number is the same. All right, so now we have the three components entered. Let's say OK. And the first thing ChemCAD does is to start its thermodynamic wizard. This is very helpful usually because it helps us decide what the conditions are going to be and what would be appropriate phase equilibrium models for it. What we need to put in something like the temperature min and max. I think 1 degree C is a good minimum temperature. As I recall, N-butanol boils about 117 centigrade, so let's put in 120. That should not be a problem. Pressure is going from 1 to 10 bars. That should be okay. So I think this would be good. And it selects for us NRTL as the way to get the partition coefficients and the enthalpy will be given by latent heat. We'll take a look at that when we say OK. Here we can actually change the thermodynamic model. The program suggests to use NRTL. We don't have to do that. We'll come back later and see what effect that has. Because we're at moderate pressures, we shouldn't need any fugacity or Poynting correction, so we'll just say no correction here. We don't have any sour gas or SRK solvent packages. This is not going to be a very difficult separation. This will be a vapor-liquid system. We don't have water in this case. We're not doing a analysis of data sets to get coefficients, and normally I check this to reflash the input streams. So that's the partition model. The enthalpy model is latent heat. It's going to use the Dipper ideal heat capacity, and if we had water in there, it would get the water information from this improved steam tables. So we now have set the thermodynamic settings. There they are. There are the three components. What we're going to use as VLE, and all the data is imported from a previous version of ChemCAD. Okay. Now we're ready to start building the project. So let's start by putting in a feed. So what we're going to do is just click on that, pull the arrow over to the window, double click, place it in place. What we'd like to do next is, we know we're going to want a heat exchanger. This stream is going to come in at about 20 C. We're going to put in a couple pieces of equipment first, starting with the feed and then the exchanger, and then we'll start building the stream conditions. So let's try to find a heat exchanger. I happen to use the system color because it's a little bit easier to see, but you can do whichever one you want. So here's a heat exchanger number 1. If you need to have some more information, if you right-click on the icon, you will see a bunch of different choices. In this case, we're going to keep it simple. We're going to use heat exchanger number 1. We're going to bring it over and put it on our process flow sheet. And click it, and it's in place. Now what we'd like to do is connect these two. And so I just need to find the red dot, connect it to the blue dot, and there we have our first connection. Sometimes I'd like to adjust these so that I have straight lines. I don't have any nooks or crannies in the entry lines, and so I'm just using my spacer tool to bring that down a little bit. Now we'd like to specify stream 1. So let's notice that as soon as the mouse goes over the stream, I get information about what's in there. There's nothing in there now. When I double click, there we go. So I'm going to name this mixed feed because it's got a bunch of things in there. I'm going to say the temperature is 20 centigrade. Pressure, I'm going to put it 1.4 bar. I'm going to pump this a little bit. I'm not going to worry about the vapor fraction. I'll show you how to adjust that in a minute. Let's look at the flow units. I would like to actually use mole fractions just because it's easy. I happen to have the information on that. And I'm going to use as a flow unit something that's also convenient, kilomoles per hour. Now probably if we were getting this problem from our polymer client, they would likely better know the gallons per hour of their stream, and they would also know the weight fractions or maybe the volume fractions of what's there. In this case, we'll just use the mole fractions because this is sort of a made-up problem. So we'll put in 0.0498 mole fraction of methanol. We will put in 0.50 mole fraction of isopropanol, and the remainder is going to be N-butanol. Just a touch, and that should, if I've done that right, that should be 100%. What we'd like to do is we would like to check to make sure that this is a liquid and not a vapor. So I'm going to use this nice little tool here, which we'll use a couple more times when we do this problem, which is to flash it. So if I just click on that button, it will do a flash calculation to determine the vapor fraction and the enthalpy in millijoules per hour. So there's a flash calculation. It says that it is a vapor. If I wanted to feed a, excuse me, it says this is a liquid, the vapor fraction is 0. I could also determine when this would be a vapor if I keep the pressure the same. What I'm going to do is take the temperature out. I'm going to put a vapor fraction of 1. And now when I do a flash calculation, it should tell me the temperature at which I would have to raise the stream so that it would flash. And it says it'd have to be up at 84 degrees centigrade. Okay, so this is going to be a very useful tool. We'll have it several times today when we're talking about this problem. So let me go back and reset these conditions, if I can. Take out the vapor fraction, put in the actual temperature we expect. Okay, we'll flash it. Okay, vapor fraction 0, it's all liquid feed, that's great. Okay, now we're ready to put in a distillation column. There are several choices here, and I'm going to show you a couple of them. There's one that we are not going to put in. For many columns, we might start with a shortcut distillation, and this gives you a little bit of explanation for it. What it does is use the Fensky-Underwood-Gilliland model to simulate a simple distillation. This is not going to be very well represented by these kinds of equations, so we're going to skip it for this problem, and we're going to go on to another one, which is tower. And I'm going to right-click this, and you see there's a whole bunch of different towers. We're going to just use tower 1. That's good for us. So we'll bring it in. Here's tower 1. And we're going to feed tower 1 at the very top. This is going to be tray 1. ChemCAD labels the trays starting at 1 at the top and down to the highest number at the bottom. So let's go ahead and click on this. No, sorry. Now we've got it. Now let's connect it. Didn't quite get it that time. Let me try it again. There we go. Okay, that's connected. Now I'm going to put 2 product streams in, and then we'll set conditions here. Here's the overheads product, and this product is going to be a mixture of methanol and isopropanol. And then here is the bottoms product. This product should be mostly isopropanol if we do things properly. Okay, we got that connected. That's the top stream. Here's the bottom stream. Okay, so we now have 1, 2, 3, 4 streams. Now let's set the conditions. Normally I go to each unit operation, set the conditions, run it to make sure it runs, and I have output, then I go on to the next. This helps debug the program, and it's usually faster for me than putting in all the equipment and then starting to run it and then try to start to debug it. So let's go into the heat exchanger. We need to set this pressure drop. Typically for these kinds of exchangers, there might be a 3-bar drop. We could look at the heuristics in the design textbook for that, but 3 3 psi would be right, so it would be 0.2 bar would be about right for the pressure drop. The temperature we want coming out is going to be the approximate temperature of the top of the column. Because I've already solved the problem, I know what that should be, and it's going to be about 69 C. So I'll just say 69 C. Click OK. Utility rating, we'll take a look at that as well. We're not going to, at this point, figure out what the utilities are. We're just going to size this and get a total heat load. And we are also not going to look at the cost estimation. This will be a shell and tube. Typical carbon seal would be fine. So let's go ahead and click on that. Let's go ahead and, since this is highlighted, we can now run the operation. So we'll go to the run stage and we'll say run. And we're going to, say run selected unit ops, which should be the heat exchanger. Okay, the run started and it quit. So we should have some output to stream 2. And there's stream 2. We have a pressure of 1.2 bar. The pressure dropped because we had a pressure drop in the exchanger. The temperature is now 69 centigrade. And notice that we have pretty small flow, so I need to go back and check this stream because there's something funny about this stream. Let's try to specify this again. Okay, yes, the total flow I should have put in here would be 100 kmols per hour. There we go. So let's try flash that and make sure it is happy with that. It is. Now let's go back and run this heat exchanger. We should get a much better answer. Let's see, I think we can also run it a different way. Just by right-clicking on it, you can run it by itself. It started, it is now completed. And so now we have 100 kmols per hour. Here are the flow rates for the methanol and the isopropanol and the N-butanol in kilograms per hour. That's great. Okay, so now we have the fun job of specifying the distillation tower. This is the tower number 1. Double click on it. We would like to have a total condenser because that's going to help us add the add a stage. We're not going to worry about a subcooled temperature. The top pressure, let's set at 1 bar. And then I'm not quite sure what the condenser pressure drop is going to be, but let's suppose it's 0.05 bar, and let's suppose that the column pressure drop is like 0.05 bar. The number of stages is going to be 10. We have 10 trays. We have a total condenser. We have a partial reed boiler. And the feed tray could be, well, it could be stream 2. That's feed tray for stream 2 would be something like 1. Let's take a look at the specifications of the column. Okay. So here we have to specify the conditions here. We have a number of different choices. We have many choices. Let's start by specifying the reflux ratio. There's a good reason to do that, and that is typically for many systems, a reflux ratio of 1.3 is fairly close to optimal. If we go lower, then small changes in the reflux flow rates can make big changes in the performance of the top of the column. If we go much higher, then we will be using a lot more heating and cooling throughout the column and really increase the cost of running this operation. If we start increasing the cost because we have high utility usage, the toll processor will lose his or her shirt because they've already paid for the equipment. Their biggest cost is going to be the utilities and the labor for this process. So let's go with 1.3. We can go up and down later. Let's put a reboiler in there too, shall we? Let's actually set the bottom mole fraction. Because what we'd like to do is we would like to say that the isopropanol is fairly pure. So we can now specify what the bottom component mole fraction is for isopropanol. If it's technical grade, we need at least 99%. Let's set it at something a little bit higher than that. Let's set it at 0.992, for example. And then, let's see, let's go to convergence. Do we need to do anything there? Not much. We normally put this on auto estimation, and then it's important to check this little box here, which runs an optimization. If you happen to put in design specs which are not feasible, in other words, the energy and the material balance does not close around the column, ChemCAD will search for conditions for which the material and the energy balances close. And so you definitely want to check that in case you have overspecified or improperly specified the system. So I think we're about ready to go. There's one other thing we will look at here, which is if we're going to run a cost on this, we have to specify what kind of column it is. It's going to be a tray column, it's carbon steel, and it's a valve tray. Okay, so that should be pretty good. All right, so now we should be ready to run this unit op. So let's click on this, say run unit op, and it ran. So we really should have some answers here. Let's take a look at the bottom stream. We set that to have lots of isopropanol. And so it looks like it does have lots of isopropanol. Let's take a look at the top stream. Yes, that's got all the butanol in it. There's something funny about that. But we will address that shortly. Let me take a look here. What do we have here? Yep. Okay, let's take a look at a couple of things. One of the things we could have done earlier was to do a temperature pressure XY diagram. Let's do that now just for fun. Here's methanol as the first component. The second component is isopropanol. It's constant pressure, and we'll set the pressure at 1 bar. Let's see if we can then, we want to display the text, we want to plot an XY in a TXY diagram. So let's do all that. Boom. Okay, so here's the data. Let's take a look at the TX diagram, and then this is the one we're used to using with the methanol liquid mole fraction and vapor mole fraction going from 0 to 1. Our feed in the column is going to be right about here. And so let's take a look to see how well we would have done if we'd taken a typical approach and fed the column in the middle with a 50% split of methanol and isopropanol. Let's just step off some trays. Let's go up to 1, 2, and a little bit more would have given 80% mole fraction in the distillate. Let's go down 1 step, 2 steps, about 20 mole fraction in the liquid. So if we were feeding this in the middle of the column, we're going to be in trouble. Where we did decide to feed it was at right here at the liquid mole fraction of 0.5 at the very top of the column. So let's go down 4. 1 stage, 2 stages, 3, 4, 5. Whoa. And you can see that as the equilibrium curve gets closer to the 45-degree line, we're going to have more and more of a challenge attaining the 1% methanol in the bottom here. Okay, so you can see what the challenge is. We really have probably not enough trays for what we want to do, but we're close. Okay, so let's run this whole thing again, and good. No warnings, no errors. Let me check this one more time. Yeah. What I'm going to do is I'm going to go now to I'm going to close this file. I'm going to save it and close it. Let's close all these too. We don't need them. So here is the file I have made before for this problem. We'll zoom it to fit. There we go. We'll run it. We'll check this bottom stream. Oh, good. That's where the butanol is supposed to be, and it's there. That's great. Let's check it on a mole fraction basis. In this particular case, I think we specified 0.991. That was not the case on the other diagram, but it's the case here. So we have a little bit of a methyl alcohol, and then we have essentially all of the N-butanol in the bottom stream. That's where we want it. We want to get it out of the process. This is a technical grade isopropanol that should be saleable as long as the customer can handle a little bit of N-butanol and methyl alcohol as low-level contaminants. The overhead product, let's take a look at that. I'm going to get it into mole fraction if we can. There we go. It's about it's about 60-40 methyl alcohol to isopropanol. This could be going back to the client. They could adjust the stream by adding some more isopropanol to get to the 50-50 blend that they use in their operation. And so we now have two products, one that's sellable and the other one which is recyclable for the client. That's all good news. Let's do one other thing. Let's take a look at the column profile. That's one of the advantages that we have. And so let's go to a plot. And what we'd like to do is we would like to plot unit op plots, and we would like to do column profiles, and that tells us something about the conditions on the tray. So we're going to do this for unit 2, that's our distillation column, and we're going to plot the temperature profile, the vapor flow, and the liquid flow. Base component is isopropanol, liquid phase considered. Boom. Okay, so this is the temperature profile in the column. And you notice that here on stage 4, if I went to stage 4, if I were operating this column, I should see a temperature of about just under 77 degrees C right at stage 4. And if I have a temperature reading on stage 7, I should see a temperature just about 82.7 or so. It's not coming up, but hopefully I can get it. In other words, this tool can help me as I'm operating the column in the laboratory, for example. There's another thing we'd like to do, and let's go back here. I said we could adjust the thermophysical properties, so let's do that and see if it makes any impact on our process design. So let's go into thermodynamic settings, or we could go in the wizard. So this is UNIFAC. Let's change it to another choice, which could be NRTL. Here's NRTL. Say OK. And it will initialize the stream. So that's what we want to do. Now let's run this again. It ran. Now let's do the column plot again. Now you notice we're going to go back and forth between these two column profiles, but in this case we were using non-random to liquid. In the other case we were using UNIFAC. But look at the big difference between the column profiles. Typically what we would like is we would like a fairly linear drop in the temperature as a function of distance down the trays, because that means there will be less large adjustments in temperature as I'm going from tray to tray. And you can see that we're pretty close to not being able to meet the spec with this particular reflux ratio, because there are big changes in the column. We really need a straighter profile than we've got here, and when we use the other thermodynamic model, it's worse. So a key question for us in doing this distillation is, what is the model we're using for the phase equilibria, and is it the best choice for these particular sets of components? Well, I think that's enough on this problem. I think you can see how to set up the problem. Now there is good design work to do to figure out, have we optimized this system? Have we reduced the cooling water? Have we reduced the steam needs for this process? And one of the things you should be considering is, in this particular case, for example, let's take a look at this stream 6. This is the methanol stream. It's at a temperature of about 68. Obviously, we're going to store that at about 20. We need to remove the heat. You need to be thinking about ways that you could remove the heat for that. The same thing for the isopropanol stream down here at the bottom. This stream is about 84. Again, that's fairly close to the boiling point of isopropanol, particularly given the purity of that material. We need to cool that down too, and you need to be thinking about ways that you could get that accomplished. Well, thank you very much, and hopefully this has given you a good introduction to how to set up a distillation column in ChemCAD. We'll be doing some further work on distillation columns and typical process equipment as we go through these ChemCAD examples.